Nuclear power is a great idea in principle. But one of the major obstacles to its acceptance is that people are afraid of it. The idea of a runaway chain reaction that can't be stopped and that might contaminate hundreds of square kilometers for decades isn't very comforting. Today I have a very interesting development to report. It's that we now have several companies working on super safe nuclear reactors that can't have runaway reactions. They're called subcritical reactors. Let's have a look. Nuclear fission reactions derive their energy from the splitting of large atomic nuclei. But how does one split a nucleus? In the stock footage, I found this terrible animation. Yeah, it's not how it works. In fission reactors, as in atomic bombs, one splits atomic nuclei with neutrons. The neutron is not repelled by the positive electric charges in the nucleus. It enters it easily. But then, once there, it pushes all the other particles in the nucleus around, and that destabilizes the nucleus. It decays. Usually it decays into two pretty large chunks that are new, smaller atomic nuclei. The important thing is, though, that for some nuclei, it decays into two new nuclei plus two or more neutrons. And now you see the magic. You start with two neutrons, split one nucleus and get energy plus two new neutrons, which split two more nuclei, from which you get energy plus four neutrons, and then you get 8 neutrons and so on. This is the chain reaction. This chain reaction can only happen if you have sufficiently many of the nuclei densely packed together. This is what gives rise to the critical mass. That's the threshold of a material like plutonium necessary to launch the chain reaction. The issue is that for a nuclear fission reactor, you don't want to explosively release all the energy, so you have to find a way to slow down the reaction. Usually one does this with some sort of moderating material that slows down the neutrons. Still, you have the issue that anything that can fail will fail at some point, and then you're back to the runaway reaction that can overheat and melt the reactor core. Engineers have come up with various clever ways to deal with the problem. In molten salt reactors, for example, if the temperature rises too much, that'll trigger a dump of the molten salt that'll cool it, and this happens without any intervention. Then again, molten salt is super highly corrosive and difficult to deal with, and that's the major reason why, despite all the talk about it, we still haven't seen any commercial molten salt thorium reactors. The new technology is now to just never reach the criticality threshold. You just shoot at the reactor core with a neutron beam, turn off the beam, and the fission tapers out quickly. It makes runaway reactions impossible. The most celebrated company working on this is the US startup Ampera. They want to build a microreactor that could generate 15 to 30 megawatt of power. So they say it's a hybrid fission fusion machine with a sealed 3D printed subcritical core that can operate for decades and is never refueled. The radioactive compound is thorium, which then breeds uranium. They have these fancy visuals for their microreactor, which is supposed to be about 10 meters long and 2 to 3 meters wide and high. It'd roughly fit onto a truck. That's the main selling point, because nothing reassures the public about nuclear power like we can put it on the motorway. But wait, just what's the fusion part? I haven't found any explanation for this on the company pages, but I have a guess. You see, the standard way to get neutrons is from a proton accelerator. You accelerate the protons, slam them into a target, and get a spray of neutrons. The problem is that these proton accelerators are large. We're talking several hundred meters in length. You don't put these on the back of a truck. Looking at the Ampera images, it seems rather clear that the fusion part must be a compact neutron source. The most efficient way to create neutrons from fusion is to use deuterium and tritium fusion. That's kind of the standard fusion process that most fusion startups want to use. Problem is that I don't see how the yield of the fusion reaction will be remotely high enough for their purposes unless they solve fusion first, in which case why use the fission part? So, well, personally, I would not invest into this company. There are other subcritical startups, though, for example, Subcritical Systems in Austin. They say that they're using a proton accelerator for the neutrons and want to bring power online by 2028. We're probably talking about something in the range of 50 to 100 megawatts or so. Given that that technology is known, 2028 seems rather ambitious, but not totally impossible. The company Muon Inc. is working on something similar. These reactors likely wouldn't be used to power cities, but you could use them to power a data center or a factory complex or similar. The subcritical reactors have another benefit, which is that one can use them to burn radioactive waste while creating energy from it. The Swiss company Transmutex specializes in this. Besides this, there are a few governmental projects in Belgium, China, and Japan. In summary, subcritical reactors could indeed make nuclear fission power much safer, but I'm skeptical that they'll be either cheap or small. Maybe the reactors can't run away. Their investors certainly can.